simplify it. Yes. If you have a question, ask. Don't raise your hand. I will not say it. I hope what I have done is clear with you.
Yes, sir.
Okay. So that is fine. So you can always, any number you can express in the fraction form are all rational numbers. What about irrational numbers? So the irrational numbers comprises radicals. Remember, we talk about radicals. Radicals like this. This is a radical. So if you are dividing radical by a whole number, it becomes irrational number. Because there's no way you can express this one in a pure fraction, in the fraction form. Although this is a fraction form, but we have the radical there. This one is not a radical. So anytime you have something like this, you cannot express this one in the rational form because this square root is imperfect square root. Imperfect square root. For example, if you have a perfect square root, then you can express it as a rational. For example, if you have square root of 25 over, let's say 2, 25 over 2, it means that you can get a proper fraction from here. So you can get 5 over what? 2. That is a rational number. But if you are going to take the square root of 2, it is impossible. You are going to get decimals. And that means that you will not qualify to be a rational number. But if you can express a rational number in a fraction form, then we can also call them irrational numbers. Rational numbers. Remember that at the senior high school level or junior high school, that we've been given some numbers that, let's say, if we have 0, let me say 1.14, let's take this one up, 1.14, and they say, no, let me write, okay, 1.14, and they say to convert this one into fraction. So here you stand here and run the number of zeros, so we start from here and say 1, 2. So how many twos, how many zeros, how many points, or how many rounds? 2 rounds. So we are going to put 114 over 100. So this is a fraction form. So we are able to convert decimals to fractions. These are all rational numbers. So in essence, we are saying that all decimals number that you can express them in the fraction form, they are all rational numbers. Okay, so all these are rational numbers. All these are rational numbers. Then SAT is also another thing we learn at the senior high school. It is an example or another form of rationality or rational numbers that consists of more than one polynomial numbers or root, one polynomial root. Some of them can be considered as rational numbers. Some of them cannot be irrational numbers. So most of the SAT numbers are not rational numbers. Because if we have 2 plus the square root of 3, this is more like a multiple numbers, radicals. So we have this one and this one. There's no way you can express this one in a fraction form. So this one becomes irrational numbers, or sometimes we call it imaginary numbers. So most of the SAT numbers are not rational numbers. So all what we have done, we have been able to simplify it in the table form that you can be able to distinguish between rational and then irrational numbers. So there's no need to worry yourself. Now haven't understood what rational numbers are. We can do some small exercise. Okay. So here, if you are able to convert these ones into fraction forms, they will call it, they are all rational numbers. So express each of the following rational numbers as a ratio of 2 integers. as a ratio of two integers. So when you take 10, you have to express it as a fraction. You take -7, express it as a fraction. You take 6.3, express it as a fraction. Okay. So for example, let's take -7. How do we express that one as a fraction? -7. -7, what will you get?
-7/1.
Yes, -7/1. So this is a mixed fraction, right? -5, 1/3 is a mixed fraction. So you can convert it to either proper or improper fraction. Okay, and here you are going to get -11/2. So they are saying that all the fraction, if you are be able to express them as a fraction for all the numbers here, we can easily express them as a fraction form. And that means they are all rational numbers. They are all rational numbers. Thankfully, the solutions are there. So you just have to be looking at how you can express them. And all here. This one was 6.3. And because you are running it at once, it becomes 63 and then 10/10. Okay. So expressing or converting number to rational numbers or fraction is not difficult. We can all try to do it ourselves. Now let's try to simplify square root of a product. So when you are multiplying a square root or radicals, we need a simple rules to also do that, even though it's all boiled to 1/10 them, but the square root is also very, very important. Okay, so if you have a square root of, for example, if I have a square root of QT with QT, I can try to separate this. The square root affect all of them. The square root affect all of them. So I can decide to separate them. The square root of Q multiplied by the square root of T. They are all the same thing. Get that I want to separate them. Simplifying the square root of a product. So you have square root of numbers, you try to separate them and the rest. So that is it. For example, if you have, if I have, let's say, for this example here is 100, 360, 3,600, 3,600. You can try to simplify this in bit by bit, separate them small. You know that if you, and remember, if you are trying to simplify them, you must have a perfect square root. You must have a perfect square root. For example, if you take this number, you say that you can divide this one into 2, you can simplify into 2. 36 is a perfect square root. 100 is a perfect square root. Don't go and look for a number that is not perfect square root. You'll be stranded and you cannot go ahead to simplify it. Look for two numbers that are what? Perfect square root. Then you do it and go away. Okay. That is it that we have to do. So any number you are giving, anytime you are giving a number, try to simplify it by using the product, then you can move on to do the simplification. These are all examples. One example is the square root of 72. Now, if you look at 72, you have to look for a perfect numbers that if you multiply them, you are going to get that square root. In most of the time, you might get mix of them. You might get some of them to be perfect square root, some of them to be what? Imperfect square root. But it's better you get some to be perfect and some not to be perfect than to get all of them to be imperfect. That would be a problem for you. Okay. So if you look at 72, you see that we broke the 72 into so many subsections. We know that if you multiply 72 by 9, and divide and also multiply that one by 2, we are going to get 72. So we have two perfect square root there. 4 is a perfect square root. 9 is also what? A perfect square root. Now, after that, you can now come and separate them because they are all perfect, or because the square root affect all of them. You can now say the square root of 4 multiplied by the square root of 9 multiplied by the square root of what? 2. Square root of 2. And that will going to give you 2 multiplied by 3, and then the imperfect square root. This is imperfect square root, so you cannot do anything about it. So you just leave it like that. Okay. And that will eventually give you 6 square root of what? 2. So whenever you are given something to do, try to always simplify it before you move on to do the rest. Okay. So again, if we are also given this one, we've looked at them already. Sometimes you try to simplify the square root of powers, by applying the radical sign to them. Okay, so for example, you know that if we have q raised to the power 4, you are taking the square root of this. We are trying our possible best to simplify the power here. It tells you that if you apply the square root here, because this square root is the same as half, it will go to take half of it. It's going to take half of the 4. So in that sense, we are simplifying it to give you square root of what? This will give you q raised to the power 2. We have looked at this already. It also tells you that if you have 3, if you have x raised to the power 6, you can also simplify this root, square root here. Remember, you can use 2 things. First, you can remember that we were looking at the law of indices. Is it the second law or first law of indices? We said that if we are multiplying 2 numbers and the base are equal, we add the exponent. So it means that when you have 6 with x raised to the power 6, because x is the same base, it means that they had already multiplied them. So it was this x raised to the power 3 multiplied by x raised to the power 3. So the law of indices are saying that because the exponent, the bases are equal, you add the exponent. So we are going to get x to the power 3, 6. So it means that the square root of this one is going to divide this one into 2, and that will give you what? The 3 that we are having here. So these are also something that's simple that we all have to, not something that we should worry about. For example, here we have this place, square root of x squared raised to the power y, square root of x squared 4 raised to the power 4, y raised to the power 4. So in this case, the square root of x squared y raised to the power 4. In this case, we can apply the square root here. We can simply say that the 2 eventually go away, and we divide this one by 2. And that is going to give you what? X y squared. Okay. So all these are not something, it's a basic thing that we need to learn. It's a basic tool that we need to understand, but we need to apply them as we move on. Okay. Now, these are, I guess, examples that we can try. You can try your hands on. The question is find each square root through simplification. So we are giving you 1,600 to find this, to simplify it. So you have to look at perfect numbers or perfect squares. Don't get look at any number. Look at perfect squared. If you look at this one here, you can simply think of the perfect square is 16 and 100. This is the perfect square. So that you can say that these are the square root. 25. So once this is the perfect square, it means that you can separate them. Square root of 16 and then square root of what? 100. And this is going to give you 4 and 10. Or you are going to get 40. Okay. So there's always a way to simplify them. Just try to look for numbers, a perfect square, to break them down. To break them down. So like what we said, the second one was what? 256. So 256, we can break it down by 2 perfect squares. That is 4 and then 64. Always look for the perfect squares. Always look for the perfect squares. Okay. Don't look for the imperfect square. Look for the perfect squares first before you can do you want whatever you simplify to get your final answer. The next one was 225. It means that you have to also look for the perfect squares, 25 and 9 to give you the 225. Then the last one was 576. 576. 576. There are also 2 perfect squares. That will give you 9 and 36. So here, what here simply tell you is that whenever you are given a big number in the square root, you can try to always simplify it to the lowest level before you can get your final answer. Then just put it in the calculator. If it is exams, yes, we know that you put it in the calculator straightforward. You can give it to you straight. But if the question says, find the square root through simplification, you mean that we have to be breaking them down into pieces. You can use calculator to get all the perfect squares into pieces before you can get your final answer. Okay, so these are some of them. These are some of them. You can just go through the solutions are there. You can just go through and then look at how you can find the square root for them. Okay, then we'll also look at the square root of powers. Here, the powers, we're looking at how we can simplify the powers. Simplifying the powers means that you have 49, obviously. The 49, you take the square root of 49, you're going to get your 7, right? B, there's a B there, which is raised to the power 8. It means that the square root also affects this B. And we know that the square root here is the same as 1 over 2. So it means that if we are going to divide this 8 into 2, so this one will give you the square root of 7. Sorry, the square root of 7 b with the power 4.
Please, sir, please come again.
Hello.
Yeah, please come again.
Okay. So we are saying that we are looking at the square root of a number. That is okay. First of all, let's look at if I put square root of a raised to the power 2, what will you get?
A.
A. How do you get the A?
So with that, the radical, that is the square root, is 1 over 2.
Yes.
So it's
Yes.
going to a power 2 times 1 over 2. The 2 cancel 2, so it will be.
Yes, exactly. So here is going to be A 2 this one is the same as 1/2. So here you are multiplying here by 1/2. So this 2 will cancel this 2. So you are left with only A. That's the essence. Now, if you take the B2, it's the same thing. So you are going to get B raised to power A. It means that the radical here is also 1/2. So 1/2. So that you are going, this one will go here and also go here 4. So you are going to get B raised to power 4.
Okay, yeah.
The one who asked the question, are you okay?
Yeah, I'm convinced now. I'm convinced.
Okay. So the rest, we are going to do the same thing. Like this one, 10, you are going to get C5 at the end. Here, you are going to get, if you divide this by 2, you are going to get what? 8. Yes. Here, you are going to divide here by 2, you are going to get 3. Here, you are going to, yes. So here, what about here? What about 25? So someone should do that one for me. And let's see. The square root of 25 t raised to power 3. What will you get?
Please, the question again. Sir, please.
Someone is disturbing us, so the person should come again. You are going to get
So it's going to be 5 raised to power 6.
5 raised to power 6. Are you sure?
5 raised to power 6.
Huh? Use the same form. Use this one. Use the same thing that
Yeah, it's 5. It's going to give you 5 raised to the power t 5 t raised to the power 3/2.
Yes, 3/2. 3/2. Use the same format here. You are going to get it because it's t 3. Then you multiply here by 1/2. So this one multiply then in C. You are going to get 3/2. You're going to get 3/2. So that's it. Okay. So here,
Hello, sir.
but yeah.
Hello, sir. Yeah, please. Then what about
Yes,
the 2 in front of the square root? Sir, please, what
Yeah,
about
when
the 2
you
in front
finish-
of the square root?
When you finish multiplying, then when you finish this one, if you
Okay.
finish this one like this, you can multiply this one by 2.
Okay.
Uh-huh.
Okay.
But yeah, but the other way that they've also done is that the other way they have also done here is that if you don't want to go by this, if in exam you are able to go by this, there's no problem. You are right, 100% right. But the other way you can also do is that, let me clean some parts here. The other way you should have also done is that, you see, this 3 here, it means that we can decide to factorize this 3, like this t. So instead of writing that, you can write 2, then you bring the 1t outside. Okay. Then you bring the square root here. Then you have your 25 t squared. Yes, so in this way you can easily do the away with this t, right? So that if you are multiplying the t inside, you are going to get the 3 back. So in that case, we are going to get 2t multiplied by 5t. 5t. Are we okay? So it doesn't make any difference. It doesn't make any difference. But if you want to make it, you can also do this one then. It doesn't make any difference from the other answers that we have. Okay. So they were again trying to also look at that, try the possible ways to also simplify the formula. So here what they did is that they break the t down. They break the t down into two pieces. Okay. So that if we multiply this t here squared by this t, okay, so they use this format because the t keep here. They don't want to treat it as this is, so because of the t keep here and using the product simplification of the product product radicals, one that are all in the same radical, you can separate it this way. And when you separate it this way, it means that you can take the square root of the t. The square root of the t is going to give you t. But you cannot take, sorry, the square root of the t square is going to give you t. But you cannot take the square root of t, this t here. It's standing alone. Okay. And that is why they have this e to the power t here. And remember, there was a 5 and 2 that is multiplying together. And that is what they also have here. It doesn't make any difference. It's the same thing that you do earlier on. There is still t here, there is still t here. It means that if you multiply this t inside, you are still going to get the square. And that will boil out down to whatever you are going to get. Okay. So always find a simple way of simplifying the t's that you have. Now, what about fractions? You can also simplify fractions whenever we are giving them. Fractions are also part. You can simplify them. Okay. And then I think this one too, we have done it already. So this one, they're also telling you that if you have the square root of a divided by b, all of them are under the square root. We can decide to separate them. Square root of a separately, square root of b separately, and then you can simplify them as well. This is an example. You have the square root of, let's say, 25 over 49. And because this square root covers both up and down, you can break it down to square root of 25 over the square root of what? 49. You can decide to break it down so that you get 5 over 7. Okay. So whenever you are also given fraction, we can break it down into smaller pieces before we can move on to do the fractions. And these are also examples that you can explore. The solutions are here. So anytime you make reference, when you are going through, for example, you are going through this, you can make references for the solutions are here. Okay. We can look at adding and subtracting square root of numbers. Adding and subtracting square root of numbers. This one, there's a basic rule that you have to understand. Whenever you are squaring, just a minute. A minute. Okay, so we can make progress. So here we are going to look at how we can add and subtract square root of numbers, square root of numbers. Now, before you can add and subtract square root of numbers, all the radicand or all these expressions or all numbers under the square root must be identical. Must be identical before you can add them. Must be identical before you can add them. For example, where's my pen? So, for example, if look at this, if we want to add 5 square root of 2 plus 5 square root of 3 square root of what? 2. Yes, this and this are identical. So what you do is that anytime you are giving radical numbers and they ask you to add them, always make sure that the radicand or the expressions or the numbers under the square root are identical before you can add. Either you are adding or subtracting, the rules remain the same. So once this and this remain the same, are all the same, then you can say that you are adding this and this. So you can get 5 plus 3. And because this and this are identical, you just bring one of them. Just bring one of them. Okay. So here you're going to get 8 square root of what? 2. That is all. So make sure you have the expressions inside the square root to be identical before you can add them, or else you cannot add them. You cannot add them. Okay. And then take note also that it is not always that they will give you the square root or the expression in a number to be identical. We can give you separate numbers, and you have to make sure that you simplify them to suit what you want. For example, you have 50 square root of 50 plus square root of 32. You are adding them. But we're seeing that this number 50 and 32 are not identical, so you cannot add them. So what you need to do is that you have to make sure they become identical. You have to make sure they become identical before you can add them. Okay, you make sure you become identical. So why do you do that? You look for perfect squares. Perfect squares here. And here to look for perfect square from 32. Okay. You know that the best factors, the factors of 50. So if you multiply 2 by 25, you are going to get what? 50. Okay. So the two, I have one perfect factor. Then I can now say that, well, I have, I can say the square root of 25. And then the square root of what? 2. These are two factors. Now, the square root of 25 is going to give me 5. But I cannot take the square root of what? 2, because it is what? Irrational number. So I can just write the square root of 2 there. So this is, you have simplified this one to 5 square root of 2 plus. Now, if you take 32, then you also look for 2 numbers. You have to look for 2 numbers. And those 2 numbers is, if you multiply 16 by 2, you are going to get what? 32. Okay. So it means that I have gotten one perfect square root, that is 16. So I can take the square root of 16 and square root of what? 2. Square root of 16 is going to give you 4. So I'm going to have 4 and then square root of 2. So I've been able to break this one, 4 square root of what? 2. Now you can see that they are now identical, 2 here, 2 here. So you can now add 5 to what? 4. Then you put the square root. So basically you are going to get 9, then square root of what? 2. Is anyone?
Please, what of the 32 no, using 8 and 4? Can that be possible?
8 and 4. So if you use 8 let me say 8 and 4, right?
Yes, please.
So it means that you are going to take the square root of 4 and the square root of what? 8, right? What is the square root of 4?
2.
2. So you are going to get 2 and then square root of what? 8. So look at this. The square root of 8 and the square root of 2 here, they are not identical, so you cannot add them.
Okay.
You cannot add them. You have to look for a number that you take the square root so that you get the same number so that you can add. Are you okay?
Okay, sir.
So always look for perfect square root that you can get identical numbers.
Thank you.
You're welcome.
Yes,
All right.
sir.
So, yeah. Go ahead.
So please go back to the screen. So, please, the what about, let's say we've reached 5 square root of 2 plus 4 square root of 2. Then what about the square root? We brought it like 1 over 2. Then we cancel the 2 out of 2. Then the second square root of 2, we bring 1 over 2. Then we cancel the 2. Then left with 5 and 4. Then we add them.
Oh, I don't
Also
I don't
possible.
get what you're trying to communicate. I'm not getting what you are trying to. Can you come again?
Where you yes, I'm talking. When you have the 5 square root of 2 plus 4 square root of 2.
If you have
Yes, I'm saying
someone okay,
5
you
square root of 2 plus the
5, okay,
square
5
root of 2.
good 2.
Square root of no, where you've marked the same square root of 2. I'm talking of what about we remove the square root and bring 1 over 2 to cancel the 2. Is it also possible?
George, you beg.
No. You see, this one is not. This one is like standing alone. It is not over. This is not square. So if you bring one, if you bring
Over
the
2,
half here to, you cannot cancel it. You cannot cancel it because this is any number standing alone is 1. So you are going to get 1 here, multiply by 1 over 2. Okay. So how are you going to cancel the 2 out? So at the end, you are going to get 1 over 2. So you cannot cancel it out. That is why we are using it. Okay. Any question before we are moving on? Okay. Now, what about combining radicals? What we did here was subtraction and addition and subtraction. It's the same thing. And now we are now trying to, it's the same examples. We can look for these examples where you can subtract or add them. Where you cannot, don't worry yourself. So here, likely all of them are, see here, there's 2 here, there's 2 here, you can add. Also see here, there's 3 here, 3 here, you can subtract. See here, 6 is here, 6 is here, you can add. 5 here, 5 here, you can add. 2x here, 2x here, you can add. 7 here, 7 here, you can add. A here, you can subtract. Y here, you can what? Subtract. So it means that whenever we give you any question on this form, make sure you look for a perfect squares that you can get the radicand or the number or the expression inside under the square root to be identical before you can do your simplifications. The answers are here as well. Okay, so this is the example that we gave, combining the unlike radicals after simplification. So some of these things like this, look at 5, look at 20, and look at 45. How are you going to add this? Look at this place, 7 and then 12. So let's look at the first one here. It means that you are going to follow the 5. You have the square root of 5 here. for you to be able to add them, it means that the rest of them should be square root of 5 before you can add. So what will you do to 20 to get square root of 5?
4 times
4.
5.
4.
Yeah, 4 times
4 times what?
4 times 5.
4 times 5. Good. So it means that you are going to get, 4. It means that you are going to get the square root of 4 times 5.
Times 5, yes.
So at the end, what are you going to get? 2 square root of what? 5.
2 square root of 5.
Yes. 2 square root of 5. So here you are going to get 2 square root of 5. Sorry.
5 times 9.
What about the second one?
5 times root of 5 times 9. So you are going to
Yes.
get 3 root of 5.
Yes. You are going to get 3 root of what? 5.
Root of 5, yes.
Yes. Yes. So always try to break them down. Break them down before you can add, or else you cannot add them. See, here is 5, here is 5, or else you cannot add them at all. Try to make them all equal before you can try to add them. The examples or the solutions are there. All of them have two solutions. So try to, if you find any something, you just make reference and look at how it is being done. Okay. So it's the same thing, addition and subtraction of numbers and radicals. We are still there. We have been able to break them down into a lot of pieces. Okay. So now this unit has ended. So we are going to look at some few applications. And we are done with this unit. Okay, the application, I'm just going to look at a few of them. You have them on your slides. You can always refer to them. So let's look at application of the function, that linear function that we did. And look at the example. Look at this example. Remember all what we have done, from linear equation, from systems, from radicals, from root, from indices, logarithms, rational, irrational numbers. You have to remember all of them because we are doing application. Now, let's look at this application. An anti-clock drag. An anti-clock drag can be made for $10 unit per unit. Anti-clock drag can be made for $10 per unit. It means you can produce this anti-clock drag and sell it $10 per unit. Now, the total cost to produce 100 units is $150,000, $150,000 or $1,500. That is the amount we can use to produce 100 units of the drugs. And to produce 100 units of the drugs, we can sell one per unit. We can sell one as $10. Assuming that the cost function is linear. The cost function is linear. So they are referring you to the linear equations. Assuming the cost function is linear, find the rule. You need to find the linear equation. Find the linear equation. Now, let's go back to application. We are now applying. What is the equation of a straight line? Is equal to, equation of a straight line is equal to mx plus c. This is a linear equation. Please, we are doing application, so please pay attention. This is a linear equation, and they are also asking you that, assuming the cost function is linear, you should find the equation. Now, whenever we are looking at linear equation, we can now look at, let me write this. You have to know what the variable stands for. This variable here stands for dependent variable. Y. What is M? Who can tell me what M is? In a linear equation, what is M?
M is the independent.
M is the
Independent.
oh,
M is gradient, sir.
Gradient, yes.
gradient or M is gradient or oh, M is the gradient or
The midpoint.
the midpoint or
Intercept.
no, that is not intercept. Have we heard of slope before?
Yes, sir.
Have we-
Yes, sir. The slope. Yes. Yes, boss.
Yes. So M is either the gradient or the slope.
Oh, okay.
The slope, and then C here is the intercept, or in economy we call it constant. We call it constant. Now, because we are, this is a mathematical framework. Now we want to translate this linear into one economics. We are talking about a cost function, a cost function. So I want to represent C as a cost. Now we are also saying that what is the cost incurred? What product are you producing? We are producing anti-drug clot, anti-clot drugs. That is, and we sell it per unit. Now the per unit here is the X, is a variable. So we are saying that to produce X unit, so we have to put this one over 100. Sorry, X. X. So to produce X unit, the total cost, this is the total cost, and this one must be equal to, we are saying that MX plus our C. Now let's take a look at them one after the one. Now when we talk about the slope, we are talking about the changes in output or marginal. We are talking about the marginal. So here, when we talk about the per unit output, we are simply referring to the additional price that we are going to get. So this this thing here represents the slope. Oh, someone is disturbing us. So the 10 here is representing our slope. So M is equal to 10. M is equal to 10. So it's speaking about the marginal or the slope. So if M is equal to 10, then we can rewrite that X to be equal to MX plus C. MX plus C. Now, this is a constant. This is a constant. So it means that for us to be able to find the cost function completely, we need to find the value of the constant. We need to find the value of the constant. Okay. Now, what should we do to find the value of the constant? We are saying that we want to produce 100 units of the drugs. Remember, I said X is the unit, X is the variable. So this is what we are producing. We are producing 100 units. So X is what we are producing. The output we are producing is X. So it means that this unit here is equal to 100. This X here is equal to 100. So if this X is equal to 100, we are also saying that how much will it cost us to produce 100 units? It is going to cost us 1,500 to produce 100 units. So the total cost function, the total cost here is going to give you 1,500. So the cost here is going to give you 1,500. So C e to the power X is going to give you 1,500. That is how much it's going to cost us. So in all, we are going to get, if we want to substitute, we are going to get 1,500, which is the cost of producing the item, is to be equal to 10. The 10 here is the slope, which is also the per unit of the unit. The per unit of the what? The cost produced. We have the 10 there. And they were also saying that we are going to produce 100 units of the drug. And they say 100 units of the drug is the X, which is 100. So we multiply here by 100. Then plus our C. Plus our C. Hold on, let me pick this one. Hello? Yeah, have you closed? So when you get to the first block, the first D block, the second D block, you call me. The faculty of law, no. Faculty of social sciences. Yeah, faculty of law side is the same block. Okay, when you come forward, I'll for you. Okay, so here we are going to find the value of C. Find the value of C. So obviously, we are going to get 1,500 is equal to 1,000 plus C. So that you can find the value of C. The value of C is equal to 1,500 minus 1,000. And that is going to give you C is equal to 500. Now, if C is equal to 500, then you can now write your full equation. You can now write our full equation. So our full equation now is C, which is the cost function, is equal to 10x plus 500, because our cost is now 500. 500. Okay. So this is the equation that they need. So this one is a linear equation of the cost function. So you take note that this is application. So you have to always read the question well. They say they are producing, they produce a drug that can be made for $10 per unit. The per unit is the item produced, and they're going to sell it for 10 units. So that will give you the marginal or the slope or the gradient. The total cost of producing is what? Producing 100 units, which is the X, is 1,500. So the 1,500 is the cost itself. So you need to find the cost, the function first, before you can also find that. So we've done that already, and then the final answer will be given to you in this format. Okay. So this is the final rule. It's the same thing that we have also been able to find out. Okay. Any question here?
Sir,
Yeah.
after solving, we came back using 10x plus 500. Can you explain that for me? I was
Come again. Come again.
After getting the 500.
Yes. So after getting the 500, you see,
Yeah.
I said the function is C is equal to 10x plus. Now C is now equal to 500. C is now equal to 500. You have to substitute the C there. You have to substitute the C, which is 500, into the equation, and that will give you the full equation. That will be C, which is the cost, to be equal to 10x plus the 500 here. And that
Okay.
yeah. Now, you see, under cost function, we have what we call the variable cost and then the fixed cost. Now, the variable cost is costs that are being incurred in variable input, like raw materials, labor, and the rest. And that is what we have here. Then what is the fixed cost? The fixed costs are also a cost incurred on fixed input, that like the land. So that one, there's nothing or variable attached to it. And that is why this one is referred to as the fixed cost. So the total cost is equal to the variable cost plus the fixed cost. And that is why we are having this function here. Just a minute, I'll be with you. Just 1 minute, and I will come back. Hello, please don't leave. I'll be with you soon. Don't leave. Just 1 minute. Hello.
We are here, dog. We are waiting. We are here.
Okay.
Are you guys there?
Yes, dog, we are around.
Yes,
Yes,
dog, we
please.
are around.
Yes, we do.
We are here.
Yes, shall we continue?
Yes, please.
Hmm. Someone was asking a question on this, or the person was okay. You can continue. Okay.
Hello, dog.
Yeah.
I wanted to know if is it always that the unit is always the slope?
No. But there's if something is, they can put it in different form, then you will be clearly, you'll be able to know that this is talking about the slope. If it is not this form, but they can also put it in different format that you know that clearly this is talking about the slope.
Okay, dog. Thank you.
Yeah. Okay. So the rest of the thing that we are going to do is just practical. That is, it's practical on how to plot graphs. So this one you find like that we can plot the cost function in the graph. So if we are given this, for example, the rest of the application is to plot the linear graphs. If the slope is negative, how will the graph behaves? If the slope is positive, how will the graph behave? Okay, you all know that if the slope is, if it is negative, we have a downward sloping. If it is positive, you have an upward sloping. Okay, for example, here, look at this one. You can sketch this diagram well. You can sketch this one very well. Here, take y has been given, but x value have not been given. So you have just to look for the y value and x. You assume any x values. So for example, you have this one. You can say you have your y, your x values here. Then your y values, y is the same as y is minus 2x plus 5. So you assume any value of what? X. And that is the simplest way to always do is use the y-axis. Okay. So you can assume that at the y-axis, x is equal to 0. Then at the x-axis, y is equal to 0. Oh, sorry, y-intercept. At the y-intercept, x is equal to 0. And at the x-intercept, y is equal to 0. So you can assume those simple words and then use it to plot your graph. Okay, so this one, instead of going through this stress, I can say that if or when x is equal to 0, what will be the value of y? So if x is equal to 0, y will be 5. So I have two coordinates, x to be equal to 0 and y is equal to 5. I can also say that if y is equal to what? 0, what will be the value of x? So in that case, you are going to find the value of x by equating them, by saying that 0 is equal to 2 minus 2x plus 5. So that you can set 2x be equal to 5. So x is equal to 2.5. 2.5. Okay, so that I can have my coordinate x to be equal to 2.5 and y is equal to 0. So I can plot this coordinate on the graph. Then I'll be able to get my graph that I want. But you want to go systematically, you can always assume values of x and then you can get the value of y. Then you can use them to plot them in the what? Y and x coordinate. So the rest of the application is just how to plot these graphs. Now, if the graph is if the slope is negative, then you are going to get downward sloping. See, you will add this one, you see that it's downward sloping. Okay, but if the graph, if the slope is negative or positive, you are going to get a positive what? So let's assume that this is y is equal to positive 2x plus 5. So the graph is going to look like upward sloping instead of what? The downward sloping that we found earlier on. So always take note of the slope or the slope of the function. Then you can use it to determine the dimension of the slope or the curve. Now, like I said, the rest of the terms is just going to be application. They are asking you to solve for this. Oh, this one is what you know already. Solve for 5x minus 6 to be equal to what? 3x. You are solving for this. You just have to group like terms. Group like terms. So you're going to be 5x minus 2x, 3x is equal to what? 6. So you have 2x is equal to 6, and then x is equal to what? 3. Solving this. It's a linear equations. Okay. It's a linear equations. There's a lot. This is another example. You have to solve. You have to solve. So you can solve this equation by finding the LCM. The LCM is 4. So it means that you are going to multiply this by 4, multiply the whole of this one by 4, multiply the whole of this one by 4, and also multiply this one by 4. So you are going to get.
Hello, sir.
Yes.
Please,
go ahead.
What makes the equation linear equation? What will I have to use to identify that this is linear equation? Yes.
Okay. So this equation is linear. Yes, I'm coming. I didn't explain whether it's linear. I'm just so this equation is linear. This equation is linear because first we don't have exponentials. You don't have exponential. The exponential here is 1. And you can even convert this fraction into a linear one. Okay, so convert this one to a linear function first before you can solve. Again, it is linear because there is no square or there's nothing like square or something here. It is not polynomial, so definitely it's a linear function. And you can demonstrate that by making sure that you convert the fraction into linear form. And how do you do that? You look for the LCM. The LCM is 4. So you multiply the whole function by 4. And that is what we have done here. Multiply the whole function by 4. If you multiply the whole function by 4, it tells you that this 2 here can go here 2 times. This 2 here can also go here. That is 1 times. Okay. And you are also multiplying by this one. That will give you what? 4 by 6. So in that case, there are 2 left here. So you are going to get 7x plus 3 minus, if we also multiply here, we are going to get this 4 is going to cancel this 4. We are going to leave with only 1. This one will remain the same. 9x minus 8. And this is equal to what? 6 multiplied by, that will give you 24. 24. Okay, so we are trying to convert the fraction into something linear, something simple that you can solve. Something simple that you can solve. So here you can now multiply this one inside. This multiplied by this. This one multiplied by this. That will give you 14x. 14x. Then this one multiplied by this, you are going to get plus 6 minus 9 plus minus 9x plus 8 is equal to 24. Okay, so you are just simplifying them. This is 6. Okay, so this one and this one, is going to give you 5x. So you are going to get 5x. And then this one and this one is going to give you plus 14. And this is equal to 24. So here you have been able to transform it into what? A simple linear function form. A simple linear function form. You can compare this one to the cost function that we did earlier on. It was C was equal to 10x plus what? 500. The same format that we have here. So sometimes we give you the fraction, we just have to simplify it, then we have to then go move on to do it. You can see here to solve this one here. You have this one is in terms of it's a linear function, but it involves quadratic forms. It's involved quadratic forms. So you guys have to expand this one, then simplify, then you also get your answers as you go. So the rest of the 10 that you are going to do is applications. So there's no much thing to do here. So just go through. If you have the slides, just go through the applications. Then you'll be fine. Okay. So if you go through the application and you have any problem or anything issue that you can let me know, because the rest of them are just applications for you. So go through them yourself, and let's move on to the unit 2, unless you have a question here to ask. I'll just introduce the unit 2, then tomorrow we take it from there. But tomorrow we are meeting again, and then we can do more on the unit 2 tomorrow. So I just want to introduce you to unit 2. After introducing it to unit 2, I'll send the slides to the course web. So for you to go through before tomorrow. Can you see the slides?
Yes, we can, sir.
Yeah. So this is the unit 2 that we are going to do, God willing, tomorrow. All things being equal, let's pray nothing happen tomorrow. Tomorrow I'm available, so I can be able to meet you tomorrow. So we are going to look at
Lisa, I can't see the slide though.
Who can you see? You can see the slides?
Yes, please.
Who can confirm?
Please check your network.
Yes, kindly check your network because we can see.
I can hear your voice clearly, but can't see.
Oh, then Solomon, check your connectivity because others can see. I can even see that someone has written on the text box that almighty calculus. Someone said almighty calculus. Oh, it is not going to be deep one. Don't worry, you'll be fine. It's just going to be something that we don't have to worry. We are going to finish unit 2 tomorrow. Don't worry. It's something basic. It's just basic thing that we need to do. Okay. Now, what do we expect tomorrow? We are going to look at the outline briefly. We are going to look at presentation, finding the gradient of nonlinear function, finding the limit, finding the derivatives, differentiation of function of one variable, higher order derivatives, differentiation of function of more than one variable. So basically, this is not something that we should worry about. Tomorrow we are going to finish it sharp. Okay. Then here don't worry, because tomorrow here the calculus here we are going to look at is basically differentiation and derivatives. We are going to look at the rules of differentiation, the property of differentiation. That's all, the rules. What do you have to do? Quotient rule, product rule, chain rule. When are you going to use them? When are you going to apply them to do your differentiation? The basic rules of differentiation, the power rule, the addition rule, and those things. So it's not going to be something that you should worry yourself with. Okay, so guess before you go, you see this word calculus. When we talk about calculus, okay, we are talking about two things. We are talking about differentiation and we are talking about integration. These two things constitute what we call calculus. And this calculus was far being used by the famous scientist Isaac Newton, which we all aware of. He developed this calculus when he was trying to study the magnitude of changes between functions or movement between functions or movement between substances. So he wanted to look at changes, whether functions or systems of functions changes over time or move over time. If the functions are linear, how the changes are also how the movement take place. If the functions are non-linear, how they also take place. So he was trying to find out the changes or movement. So when we talk about calculus, mathematically, we are talking about how we can apply changes or movement within a function. Okay. So like I said, many years ago, we've been using it. So basically, when we talk about calculus, we are basically talking about differentiation and calculus and what integration, and they are intertwined. They are opposite. If you know how to do integration, then automatically if you know how to do differentiation, then integration becomes something applicable for you. So it's not something we should worry about. So, but for this semester, we are dealing with only what differentiation first. Differentiation. So differentiation essentially talk about determining the rate of changes of a function. So whether if you are given a linear function and you want to determine the rate at which this linear function changes or move over time, we can use the concept of what differentiation. We differentiate, or we look at the changes within period. This period, we look at the current period and then the next period. We want to look at the changes. Get like calculating inflation rate. Okay. Get like comparing today and yesterday. So we want to look at the difference. So we have to take the current period minus the previous period. Then we know how the movement looks like or the changes look like. So instead of using those things, we can use a simple differentiation, which was also invented by Newton to do that simply for us. Okay, so that is basically what the differentiation is talking about. Okay, so again, it is very good for. It can be used to in so many fields. First, we can use to determine. We spoke about independent variable in our first unit. We talk about independent variable. We were able to establish that when there's changes in the independent variable, it will affect the dependent variable. How do we know the changes? How do we know the movement? How do we know the magnitude of changes in the independent variable? And what is the magnitude of change in the dependent variable? We can use the differentiation to look at changes in the independent variable that can explain the variation in the dependent variable. We can use differentiation to also do that. And we can also use differentiation to also look at whether the function is maximum or minimum, whether we have a concave or convex function. We can use differentiation. We use the first order condition, which is the necessary condition to determine the critical point. And then we'll use the second order condition to determine whether the function is maximum or minimum. So time is up. We are going to proceed tomorrow. Tomorrow is 4 hours. So I believe by 4 hours time, we'll be done with this unit as well. Course rep. Is it your last?
Sir.
Is it your last week for the teaching?
We have a week.
After this week, we have a week again.
Yeah, I think that week will be for practicals. We don't do the practicals, so we can utilize that week.
Okay, that's fine. So we can utilize that week. That's fine. So and so we have done vertically like how many weeks of teaching? 2 or 3? 2.
Tomorrow will be our 3rd week.
Yeah, 2.
But the first week that we couldn't meet, will it be counted as part?
Yes, it is. It is.
So if it is, then it's 3. This is the 3rd week.
Yes.
Course rep, I need the day that we started, the first week, the date.
All right, sir.
If you can text it to me.
All right, sir. So I will do that.
All right, thank you very much.
Hello, Doc.
Yes.
Doc. Sorry, this is a quick one. Since we want to have like a past question so that we can know how the questions are said, especially for the quiz that is in 2 weeks' time, if it is possible.
Okay, I will make it available. So I will look for him. I'll pass questions for you. Sure.
Okay, Doc. So maybe probably if tomorrow is possible, we beg you.
All right, sure. I've heard you.
Thank you, sir.
Yeah. All right. So see you tomorrow for the continuation of the lecture.
Bye-bye.
All right.
Thank you. Thank you.
Good night.